Hello guys, and welcome once more to this new video in our YouTube channel. So in today's video we are going to compute the limit as x tends to 0 of 1 minus cos 3x, okay, all squared divided by x squared times 1 minus cos x actually. So the first thing that we are going to try to do actually is first of all try to substitute everywhere we see x with 0 actually, and try to see okay what actually comes out from there actually. So if we try to substitute everywhere we see x with 0, we are going to obtain, let's first of all start with the numerator. In the numerator we are going to obtain 1 minus cos 3 times 0. 3 times 0 gives us 0, so we are going to have the numerator 1 minus cos 0, and cos 0 actually is 1. So after the numerator we are going to obtain 1 minus 1 actually, which gives us actually 0 in the numerator, because 1 squared is actually because 0 squared is actually 0 actually. In the numerator we are going to obtain 1 minus 1, okay, which gives us 0, and 0 squared still gives us 0 actually. In the denominator you can clearly see that once you are going to substitute x with 0, is going to clearly give us 0, because you're going to have 0 squared, then 0 squared times all of this actually gives us 0, because cos 0 gives us 1, so 1 minus 1 gives us 0, and 0 times 0 actually corresponds to 0 actually. Once you are going to arrive to 0 divided by 0 actually, which is actually an indeterminate form actually, so we cannot conclude from here actually. So we have therefore to remove this indetermination actually, okay, yes. So same director actually move then for into the resolution of this question actually. So we know that okay, we can write it as what? We can still write the limit x to 0 of 1 minus cos 3x raised to all squared divided by x squared times 1 minus cos x as this. That is, we can multiply, okay, in the numerator we can multiply, okay, top and bottom, okay, with 3x, okay, all that squared actually. Okay, it does not change anything, because this 3x, okay, this 3x all squared and this one is going to cancel and gives us 1 actually. So doing this, I don't change anything actually. Yes, same thing for the denominator. In the denominator instead, I'm going to multiply multiply top and bottom, okay, with x squared actually. Yes, because doing this I also don't change anything, because this and this one can cancel and still gives me 1. That is, and gives me 1, and it still gives me the same thing which I had here in the denominator actually. Yes, so it implies saying that we can therefore split the limits as the limit of the numerator, okay, as x tends to 0, and as well as the limit of the denominator as x tends to 0 actually. Yes, this is a property of limits, that if you want to calculate the limit, okay, of something which is rational, it's actually the limit of it's actually the limit of the numerator, okay, divided by the limit of the denominator actually. Yes, for which if you see it much closer, we are going to realize that if we okay bring this square, okay, inside this bracket actually, okay, in the numerator, we are going to realize that we are going to have 1 minus cos 3x divided by 3x all squared. This all squared automatically, because this squared I just brought it inside this big bracket, then times 3x, okay, raised to the power 3x squared, then squared again. It actually gives us what? We are going to obtain 3 squared, which gives us 9, then 9 squared, this square which is outside gives actually 81, and same thing for x squared, then x squared, if you bring okay this 2 in as well, we are going to obtain x raised to the power 4 actually. And the denominator, we are going to realize that what if we simply multiply this x squared times this other one, we are going to obtain x raised to the power 4, and of course times 1 minus cos x divided by x squared actually. Okay, this part here actually. Yes, from which you are going to realize that what the x raised to the power 4, okay, both of them are going to cancel actually. That is x raised to the power 4, the numerator is going to cancel with the x raised to the power 4 in the denominator, from which you are going to be left with the limit. That's in the numerator, we are going to be left with the limit as x tends to 0 of 1 minus cos 3x divided by 3x squared, then all squared times 81 divided by the limit as x tends to 0 of 1 minus cos x divided by x squared actually. Yes, so here let us first of all okay calculate the upper limit, that is the limit in the numerator actually. Okay, yes, so how then can we determine this limit actually? Of course, if you try to substitute x, okay, if you substitute everywhere you see x with 0, you are going to realize it's still going to give us actually it's still going to give us actually if you try to substitute that actually, it's still going to give us an indeterminate form actually. So we have to as well at this level break down that indetermination, because if you substitute 0 directly, you're going to obtain 1 minus 1 in the numerator, or 0 actually, then divided by 0 in the denominator. Of course, it still gives us an indeterminate form here. How then can we remove the indetermination here at this level? Remember, we are trying to get the limit, the upper limit actually. Yes. So if we let gamma to be equals to 3x actually, we can realize that what, as x tends to 0, gamma as well tends to 0 actually. For which I can therefore write this limit as the limit as the limit as gamma turns to 0 of 1 minus cos gamma, because I let 3x to be gamma actually, and we create it as x tends to 0, gamma turns to 0. Reason why I have this here, that is the limit as gamma turns to 0 of 1 minus cos gamma divided by gamma squared, all squared, then times 81. We can consider what this actually, okay, this limit actually very important fundamental limit actually. Why? Because we know that the limit of 1 minus cos x divided by x squared as x tends to 0 is actually this also a half actually. Okay, yes. So I will leave a video. I will leave the link to the video, okay, in the description actually, where I actually proved this actually. Yes. So this is a very important fundamental limit actually. Yes. So saying that it implies this limit, that's the limit as gamma turns to 0 of 1 minus cos gamma divided by gamma squared, all squared, times 81. It's going to give us what, a half, because this interior limit here is actually a half. Then this squared times 81 actually. 1 a half squared gives us actually 1 quarter. 1 quarter times 81 gives us 81 divided by 4 actually. Yes. So actually this is actually the upper limit, that is the limit of the numerator. Okay, actually. Let us therefore move into the lower limit, that's the limit in the denominator actually. So the limit in the denominator, you can clearly see that what, very good for us, because the limit of the denominator is actually the same fundamental limit actually. So actually the limit, the lower limit actually is simply going to give us a half actually. From which you can therefore conclude that what, this limit, that is the upper limit divided by the lower limit, which actually the limit of what we are trying to look at, the limit as x equals to 0 of 1 minus cos 3x all squared divided by x squared times 1 minus cos x actually, is going to give us what? It's going to give us the upper limit divided by the lower limit, because I clearly explain how we got here actually. Yes. So the limit as x tends to 0 of 1 minus cos 3x all squared divided by x squared times 1 minus cos x is going to be the limit of the upper limit, that the limit as x tends to 0 of 1 minus cos 3x divided by 3x, okay, divided by 3x all squared, okay, then squared, okay, times 81, then divided by the limit, okay, as x tends to 0 of 1 minus cos x divided by x squared actually. You can clearly see that we already calculated the upper limit, and actually gets us 81 divided by 4, then divided by the lower limit, actually a half actually, from which you can therefore further simplify. We are going to obtain that limit to be actually equals to 81 divided by 2 actually. So thank you very much for watching, and remain tuned for a very next interesting video. Bye bye.